Alright, good morning. Today we're going to talk about section 4.2 entitled Solving Compound Inequalities. So this section 4.2, of course, is an extension of what we learned in section 4.1, solving linear inequalities. Well, the key word here is compound. We're going to be solving inequalities that are really composed or compounded with other inequalities. In particular, we're going to be dealing with or and compound inequality situations. Alright, an and type inequality, sometimes referred to as a double-sided inequality, as we'll see in a minute. Something that looks like this. Alright, minus 3 is less than or equal to 2x plus 5, which in turn is less than 7. Now, don't panic on these. I'll show you something. Really, what we're doing is taking this inequality, which we could hopefully solve pretty easily, and intersecting it, or ANDing it, if you will, with the solution of this inequality. Hence the name double-sided inequality. Alright, we do it much the same way as we solve inequalities in section 4.1. Let me show you what I mean. The goal here in these double-sided inequalities is to isolate x, your variable, in the middle and get two numbers describing milestones on either side of the number line between which the solution set lies. Right? I'm going to subtract 5 from each side of this double-sided inequality. I can clearly do that. I'll get a negative 8 on the left is less than or equal to 2x in the middle is in turn less than positive 2 on the right. Of course, now I'm going to divide all elements by positive 2. And again, when you divide or multiply an inequality through by a positive value, you leave the arrow alone. Alright, my result here is a minus 4 on the left-hand side is less than or equal to x, which is in turn less than 1. Alright, once I've reduced to this form where I've got a variable all cleaned up in between two inequality symbols like this, then we've got a solution set, and we usually label these solution sets in this fashion, in braces. Alright, this tells me x is less than 1, but simultaneously x is greater than minus 4. Right? X is less than 1, and x is greater than minus 4. Alright, let me write that down again. Minus 4 is less than or equal to x, which is in turn less than 1. Here's my solution set. What I'm really describing here is all numbers between minus 4 and 1. Alright, now this inequality statement includes an equality indicating my boundary value of minus 4 is included. And this one value up here is not included. Notice this is a strict inequality, no equal sign, so I draw an open circle at 1. So closed circle at minus 4, open circle at 1, and here is the number line graph of my double-sided inequality solution set. Alright, I've got 4 more examples of AND type inequalities, and then we're going to have 4 or so examples of OR type inequalities. Let's get on to the next one. Solve and graph solution set. Again, this is another double-sided inequality. I've got 3x minus 8 is less than or equal to 7, combined with the statement 3x minus 8 is greater than minus 5, or minus 5 is less than 3x minus 8. So I can solve both of these inequalities simultaneously, as we did in the previous example. Alright, my goal clearly is to isolate the variable inside, in between these two inequality symbols. And to that end, I'll add 8 to each piece. Well, minus 5 plus 8 is 3. 3x minus 8, plus 8, the 8's cancel, and I end up with a 3x in between. In turn, less than or equal to 8 plus 7 is 15. Alright, I want an x inside, not a 3x, so I'm going to divide all 3 pieces here by positive 3, and I leave the arrow alone. Now 3 over 3 reduces to 1 on the left edge. 3x over 3, the 3's cancel, and I'm left with x in between. That's good. And 15 over 3 is positive 5. Alright, so once I reduce it to that form, there is my solution set. X is less than 5, less than or equal to 5, and simultaneously x is greater than or equal to 1. X is less than 5, less than or equal to 5, and this statement is equivalent to x is greater than 1. If 1 is less than x, that means x is greater than 1. This really describes all real numbers on the number line between 1 and 5. If x is greater than 1 and less than 5 simultaneously, I've got all these numbers that I'll shade in between with closed dots at 1 and 5, indicating that the boundary values are included in the solution set. So here's my solution set, and here's the graph of that solution set. Again, solve and graph solution set. Here we have to solve for b, another double-sided inequality. An end inequality, really. We're asked to solve two inequalities at the same time. Alright, I want to isolate b in between, so to that end I will subtract 3 from each element. I'll get minus 5 is less than minus b. The 3's and the minus 3's cancel in between, and 5 minus 3 on the right end is, of course, 2. Now, I'm going to solve for b, not negative b, so I'm going to want to multiply each piece of this inequality statement by negative 1. And if you multiply by a negative, multiply an inequality through by a negative, both sides, you've got to reverse the arrow. It's an easy step for students to forget. So let me highlight that. I'm reversing, multiplying through by negative 1 and reversing the inequality arrow. Alright, so I'll get on the left here, I get a positive 5 is greater than, well, minus b times minus 1 is positive b, which is in turn greater than minus 2. And now some students might have trouble reading this inequality statement. Here is my solution set. This tells me two things about b. It tells me b is greater than minus 2, and at the same time b is less than 5. Please be sure that orange circle, you can interpret that as b is less than 5. So you want b greater than minus 2, that means to the right of minus 2, and simultaneously to the left of 5. Less than means left of. These are strict inequalities that indicates open circles at the boundary values, and I shade in all values in between, 5 and negative 2. So we now have our solution set to the double-sided inequality and the graph. Let's do one out of the homework list. This is number 70. This one's a little harder. Solve and graph solution set. Minus 2 less than or equal to 5 minus 3x over 2, which is in turn less than or equal to 2. Alright, clearly I'm going to want to isolate x in the middle, and to do that I need to get rid of this fraction. So I'm going to multiply all three elements here by positive 2. And when you multiply by a positive quantity, you leave the arrow alone. Or leave the arrows, plural, alone. Minus 4 on the left. In between, the 2's cross cancel. That's why I multiplied by 2, right? 5 minus 3x inside. Less than or equal to positive 4. Now we'll subtract 5 from each piece. Get minus 9 on the left is less than or equal to minus 3x in between, which is less than or equal to negative 1 on the right. Alright? Now, I'm going to divide each piece of this inequality statement by negative 3. Now, you got to be careful. Again, if you multiply or divide by a negative, you must reverse the inequality arrow. So, let me reverse that arrow. Let me reverse this arrow. And now I'll simplify. Minus 9 over minus 3 is 3, positive, right? Is greater than or equal to. The minus 3's cancel in between. I get a positive x in between. That's good. Which is in turn greater than negative 1 over negative 3 is 1/3. Now, how am I going to read this statement? Again, as before, this tells me x is greater than 1/3. And simultaneously, this says x is less than 3, less than or equal to 3. So I want all numbers on the number line that are to the right of 1/3 and to the left of positive 3. Notice equality is included here, so the endpoints are included in the graph of this solution set. Solution set here, graph here. Okay? I'm going to do one more double-sided inequality, one more AND type inequality, and then we're going to go on to OR type inequalities. Hang on, I'm going to get some trouble here. Here we go. Alright. Solve and graph solution set. Minus 4 is greater than 2/3 x minus 2, which is in turn greater than minus 6. So really, we're solving two inequalities at once. I would probably add 2 to all sides of this inequality before I do anything else. So I end up with minus 2 is greater than 2/3 x plus, minus 2 is greater than 2/3 x, which is in turn greater than minus 4. Alright? Alright. Now what am I going to do? Well, I'm going to do two steps in once here. We've been doing this, we've been doing procedures like this for some time. I'm going to multiply all three sides here by the reciprocal of 2/3. Well, that's positive 3/2, is it not? And I multiply by 3/2 because 3/2 times 2/3 will cancel out to 1x, or just x. Alright, on the left hand side, 2 cross cancels into minus 2 negative 1 times, and I get a negative 1 times 3 is negative 3, is greater than x, which is in turn greater than, well, 2 cross cancels into minus 4 minus 2 times, and minus 2 times 3 is minus 6. So this looks like a nice simple solution set. My solution set says x is minus 3 is greater than x, which is in turn greater than minus 1/6. Now if you have trouble reading these solution set statements, do what I do and look at it a step at a time, a piece at a time. This tells me x is greater than minus 6. So at minus 6 on the number line, I'm going to have an open circle because it's a strict inequality. I'm going to shade in from minus 6 to the right. But you've got to stop at a point. Where do I stop? All right, you stop right here, where x is less than minus 3. Right, minus 3 is up here somewhere. Now again, minus 3 is greater than x. That's equivalent to x less than minus 3. I can read this right to left or left to right. X less than minus 3. So I'll draw an open circle at minus 3 and shade in everything on the number line between minus 6 and minus 3. Alright, there's my number line graph. Alright, so that's 5 examples of double-sided or AND type inequalities. I want to talk about some OR type inequalities next. Now, OR type inequalities are explicitly noted with the word OR in between. For example, here I'm given 2 inequalities connected with an OR statement. So what I'm going to have to do is do what they call a set union, right, or a logic OR between the solution sets of these 2 inequalities. So what I'll do is I'll solve them both independently and then union them with an OR type statement. Looking at the left branch here, well, if I multiply both sides by positive 3, well, on the left, 3 times x over 3, the 3's cross cancel, and I have x is greater than, well, here on the right, the 3's cross cancel, and I get x is greater than 2. Alright, so I solved the left branch. Or if I clean things up on the left-hand side, I'm going to isolate x on one side of the inequality statement. I'll multiply this negative sign through this expression. I'll get minus x plus 2 is greater than 3. I'll subtract 2 from each piece. I'll get minus x is greater than minus 1. I'm sorry, positive 1. And now I'll multiply both sides by negative 1. But remember, negative 1 is negative, and I must reverse the inequality arrow. So I've solved both of my branches. X is greater than 2, and I'll connect them with an OR statement, or x is less than minus 1. So there is my solution set. X is greater than 2, or x less than minus 1. Well, in terms of a number line graph, greater than 2 means everything to the right of 2, off to positive infinity. Less than minus 1, minus 1 I'll put right here, and less than means left of on the number line. So typically in these OR type scenarios, you'll end up with a broken interval on the real number line. And here I'll label this as a graph of my solution set for the above inequality. Let's do a couple more OR type inequalities. Typically you'll have 2 inequality statements connected with a logic OR symbol. Solve and graph. Solution set. X over 2 is greater than 2, or minus 3 times x minus 2 is greater than 0. Alright, I'll solve the left branch first. Well, that's easy enough. I'll just multiply both sides by 2 and get x is greater than 4. For the right branch, I'm going to have to multiply through by negative 3 on the right-hand side. I'm sorry, the left-hand side. Alright, I get minus 3x plus 6 is greater than 0. That in turn tells me minus 6 is greater than minus 3x is greater than minus 6, subtracting 6 from both sides. And if I divide both sides by negative 3, I'll get x is less than positive 2. Maybe that was a little quick. Let me write that a little more detail. I'll take both sides of the inequality, divide by negative 3, and when you're dividing by a negative, you got to reverse the arrow. The minus 3's cancel here, and minus 6 over minus 3 is positive 2. So my solution set is x is greater than 4, or x is less than 2. Put braces around it and label it as my solution set. Alright, let's do a graph of this solution set. Again, this tells me two things about x. X is greater than 4. Well, greater than 4 means to the right of 4 on the number line. I draw an open circle at the boundary value of positive 4 and shade in all values to the right. Similarly, less than 2. Well, less than 2 means left of 2. Strict inequality means open circle here and shade in all numbers all the way down to negative infinity, left of 2 on the number line. Alright, so we have the solution set and the graph. Let's do two more. Again, these are OR type inequality statements. Solve and graph. Solution set. 3x plus 2 is less than 8, or 2x minus 3 is greater than 11. Alright, I'll take it a branch at a time. I'll look at the left branch first. I'll subtract 2 from both sides. I get 3x is less than 6, which tells me, of course, x is less than 2. Or, on the right branch, I'll add 3 to both pieces. 2x is greater than 14. Dividing by 2, I get x is greater than 7. Oh, that one was too easy, wasn't it? Here's my solution set. X is greater than 2, or I could also put set union, or x is greater than 7. And again, in these OR type situations, we can usually count on a broken interval or broken intervals of numbers on the number line. Greater than 7 means to the right of 7. Less than 2 means to the left of 2. So there's my solution set, and there's my graph. One more, we'll call it a day. Let me get a fresh screen here. This is number 67, I believe, from your homework list. Solve and graph. Solution set. X over 3 minus x over 4 is greater than 1/6. Now don't panic. Yes, it has fractions in it. We can deal with them. Or x over 2 plus 2 over 3 is less than or equal to 3/4. Now, of course, my mode of attack here is to get rid of these fractions. I don't want to deal with these fractions, and I do that by multiplying both sides by the LCM. The least common multiple of 3 and 4 and 6 is, of course, 12. I'm going to multiply by both sides by positive 12 and leave the arrows alone. Oops, a little accident there. All right, I think we can recover. 3 cross cancels into 12 4 times, and 4 times x is 4x. I also have to multiply this fraction by 12. 4 cross cancels into 12 3 times, and 3 times x is 3x. So on the left, I've got 4x minus 3x is greater than, on the right, 12 times 1 6. Well, 6 goes into 12 twice. Let me continue with the left branch here. We're almost there. 4x minus 3x is, of course, x. Well, that's convenient. So x is greater than 2 on the left branch of this OR inequality. Similarly, on the right branch, the LCM of 4 and 3 and 2 is, of course, 12. Again, I'm going to multiply both sides by positive 12, and I can leave the arrow alone. 2 cross cancels into 12 6 times, and 6 times x is 6x, plus 3 cross cancels into 12 4 times, and 4 times 2 is 8, is less than or equal to 4 cross cancels into 12 3 times, and 3 times 3 is 9. All the fractions are gone. Isn't that wonderful? All right, I'm going to subtract 8 from both sides, so I get 6x is less than or equal to 1. And of course, if I divide both sides by positive 6, I get x is less than or equal to 1/6. Now remember, you've got to connect these with an OR statement in your final solution. So I get the solution set x is greater than 2, or x is less than or equal to 1/6. All right, here is my solution set. X is greater than 2. Well, 2 is here. Greater than 2 is to the right of 2. So in my graph, I'll shade in all values to the right of 2 all the way to positive infinity. X is less than or equal to 1/6. Well, 1/6, I'm going to put, well, it's on the right side of 0. It's a positive number. I'll put it right here. And less than or equal to means the boundary value of 1/6 is going to be included. And hence I'll shade in everything to the left. Less than means to the left of on the number line. So there's my solution set, and there's my graph. Alright, so we've done about 5 examples each of AND situations and OR situations with regard to inequalities. So we'll call it a day with section 4.2, solving compound inequalities.